Okay, good morning, class Del Pilar and Rizal. As promised, this will be the recording of your lesson on infinite limits. This is for our quarter 2 lesson 5. So for this lesson, we will tackle different topics under infinite limits, starting with defining infinite limits. Then we will identify instances when the limit of a function tends to infinity and determine whether the limit of a function tends to infinity. Now, before that, we will have a preliminary activity in order for you to understand what an infinite limit means or what the concept of it means. Now we will start with this function, the limit of 1 over the quantity of x plus 1 squared as x approaches negative 1. Now you may pause this video during the playing of this video in order for you to answer the activity by yourself. So as you can observe this function, when we perform straight substitution on this function, it tends to be undefined because it will become 1 over 0. So as we earlier discussed, when a limit is undefined with straight substitution, it is usually it does not exist usually and it tends to infinity. But we will try to see using a table of values. Now we have a table of values here approaching negative 1 from the left. Now you may pause this video in order for you to solve for the values yourself, but I will be showing this one by one now. So if x is negative 0.9, the function becomes 100. And as the value of the x variable nears negative 1, it becomes 10,000, 1,000,000, 10 million, and so on. It becomes very large as x approaches negative 1 or gets nearer and nearer to negative 1. So it becomes a very large number. The same thing happens when we approach negative 1 from the right. Now, as we near negative 1 from the right, it becomes 25, 100, 10,000, 1,000,000, and then 1 times 10 to the power of 9. It becomes a very large number. So as we approach negative 1 from the left, sorry, this is from the left, the other one is from the right. So it also becomes a very large number. So as x nears negative 1, the function becomes a very large number. Now, why does the function become a very large number as x approaches negative 1? Because, as you can see, the denominator becomes 0 when x is negative 1. So, as x nears negative 1, the denominator becomes also very close to 0. As a result, the value of the function becomes very large. So what can be drawn from the behavior of this function? When a constant is divided by a very small number, the function tends to become infinitely large, whether positive or negative. Either it will become a very large positive or a very large or very small negative number. Now, from this observation, we can devise a property that when you divide a constant with a value very close to 0 or incredibly approaching or increasingly approaching 0, the result becomes a very large positive or very large negative number. Now, when you approach x approaches a value that will make a function very big or very small, it will result in an infinite limit. So an infinite limit occurs when the limit of a function is an infinitely large or infinitely small number. So either positive infinity or negative infinity. And it is written in this manner. But we must take note that infinity is not a definite number. So when we say that the limit of a function is negative infinity or positive infinity, it does not mean that the limit exists because for a limit to exist, it must be a definite number. But an infinity, a negative or positive infinity, is not a definite number. So if we have an infinite limit, it is a non-existent limit. So we introduce infinite limits only because they are crucial to finding asymptotes of graphs and other applications. Now, how do we know if the limit is has an infinite limit at that certain value of x? Now, limits that tend to approach infinity have the following characteristics. Number one, the function or the expression in the limit cannot be simplified any longer. So it either has no common factors in the numerator denominator, or the numerator is a constant. Now, upon straight substitution, the resulting limit should become undefined. Now, when these two characteristics occur, the limit of that function is most likely infinite and technically does not exist. Now, when we finally determine that the limit of that function at x, and at a certain x value, is infinite, we cannot stop there. We still have to test from both sides of the approach value to find out whether the limit is convergent, or the same sign infinity, both negative or both positive infinity, or divergent, meaning they have opposite signs, either positive infinity, negative infinity, or negative infinity, positive infinity. Now we start with example number 1. We find the limit of negative 4x squared as x approaches infinity. Now by the third theorem on limits, we can factor out negative 4 for it to become a coefficient of the limit expression. It becomes negative 4 limit of x squared as x approaches infinity. We can substitute the infinite value directly. That becomes negative 4 infinity squared. Now infinity, when squared, is still a very large number. It becomes still infinity. So we multiply negative 4 times infinity. Remember that the rules on operations of integers still apply. So since this is a negative times a positive number, it will result in negative infinity. Therefore, the limit of negative 4x squared as x approaches infinity is negative infinity. Now let's tackle example number 2. We will find the limit of negative 3x cubed as x approaches negative infinity. Now again, by theorem number 3, we can factor out negative 3. It becomes negative 3 limit of x cubed as x approaches negative infinity. Now we can substitute negative infinity to the expression. It becomes negative 3 times negative infinity cubed. Now remember the rule in squaring or raising a negative value to a certain power. When a negative quantity is raised to an even exponent, the result is positive. Now, if you raise it to an odd exponent, the result is always negative. Now, in this case, the negative infinity is raised to cube. Is cubed or raised to the power of 3. Now, this results to a negative value. So that becomes negative 3 times negative infinity. Now, negative 3 times negative infinity will result to a positive infinity because negative times a negative is a positive. So we must remember again the rules on operations of integers, wherein when you multiply values with the same sign, it will result always in a positive result. So the limit of negative 3x cubed as x approaches negative infinity is positive infinity. Now we tackle limit of 1 all over x plus 4 squared as x approaches negative 4. Now observe that when we perform straight substitution upon this function, the result will become 1 over 0 squared or 1 over 0. This is undefined, and we can reasonably conclude that the limit for this function as x approaches negative 4 is infinite. But we do not know whether it's a negative or a positive infinity. So we need to test first from both sides of the approach value to know whether that limit, what type of limit exists. Now, from the left, or we test first from the left side of the approached value. Now we assume a value that is smaller than negative 4 but very close to negative 4. So we choose negative 4.0001. Now upon testing, it will result to 1 all over 0.000000001, which is approaching infinity. Now remember from our activity that when we divide a constant by a very small number, it becomes closer and closer to infinity. Now the result is positive infinity. When we approach from the right, we assume a larger number than negative 4, but very close to negative 4. Now that is negative 3.999. Substituting negative 3.999 into the function, it will yield 1 over 0.0001 squared. Now that is again a very small number. So when we divide 1 with it, it approaches positive infinity. Since both of the limits from both sides of negative 4 are positive, then we can conclude that the limit of the function is positive infinity. Now we have example number 4. We have the function x squared plus 3x minus 4 all over x squared minus 4x plus 4 as x approaches 2. Now, when we perform again straight substitution, it becomes undefined since the numerator becomes 4 plus 12 minus 4, or 4 plus 6 minus 4, or 6 all over 4 minus 8 plus 4, which is 0. So it becomes 6 over 0, which is undefined. So we can reasonably say that this limit is undefined and will result to an infinite limit. But we need to test first both sides of the graph to find out its limit, whether it's negative or it's positive. Now, we test from both sides of the approached value 2. Now, we pick a number that is less than 2, but very close to 2. So it's x equals 1.999. Now, when we substitute 1.999 into the function, it results to 5.995,701 all over 0.000001. Now, again, when a constant is divided by a very small number, it tends to go to infinity. And in this case, it results to positive infinity since both the numerator and denominator are positive. Now, from the right, we choose a value that is larger than 2 but very close to 2. Upon substitution, it will result to 6.007001 all over 0.000001. Now again, from our activity earlier, we determined that when a constant is divided by a very small number, the result tends to reach a very large number also, and it becomes positive infinity. Now from the results, we have determined that both the left and right sides result to positive infinity. Therefore, the limit is positive infinity. Now we have example number 5. We find the limit of negative 1 over x squared as x approaches 0. Now upon straight substitution, we can see that this results to negative 1 over 0, which is clearly undefined. Now we can say that this has an infinite limit, but we need to determine what type of infinite limit it has. Now from the left side, which is x equals negative 0.001, we can see that it becomes negative 1 all over 0.000001. Since it has a negative coefficient, it will result to a negative infinity. And from the right, when x is equal to 0.001, we're approaching 0 from the right, it will result again to negative 1 over 0.000001, which tends to negative infinity. Now, since both of the limits are negative, that means they converge into one negative infinity limit. So therefore, the limit of the function is negative infinity, or negative, yes, negative infinity. Now in example number 6, we see that the limit of 1 all over x squared minus 1 as x approaches 1 will become undefined, since this will result to 1 all over 0. Now we can reasonably say that this will result in an infinite limit, but we need to test again whether both sides of the graph will result in the same type of infinite limit. Now upon testing from the left, we choose 0.0999. It will result to 1 all over negative 0.001999. Now, since this is a very small negative number, it will result to a very small infinity, negative infinity. Now, from the right, we choose x equals 1.001. Now, it's 1 all over 1.001 squared minus 1, or that's 1 all over 0.002001. Now, since the value in the denominator is very small, but it's positive, it will result in a positive infinity. Now, this results to a divergent limit since the infinities do not have the same sign. The other is negative and the other is positive. Therefore, the limit of the function is divergent. Now, in the previous examples, they have the same sign, so we call them convergent. Now, I will give these examples for you to work on. This will be your assignment. You must put this in your notebook, and we will be checking this once we return from our normal schedule of classes. We want to find the limit of 1 all over x squared minus 1 as x approaches negative 1, and the limit of 1 over x to the power 4 as x approaches 0. Now again, our summative examination will be on Monday in the class period that we will be having for each of your class. Now for Del Pilar, that will be at 8:30 to 9:30, and for Rizal, that will be from 3:30 to 4:30 p.m. So good luck everyone and good morning.